So the next talk is by Dr. Ryan Tappero from the National Synchrotron Light Source, Brookhaven National Labs. Ryan is a research soil scientist and X-ray microscopist at the NSLS-II and is responsible for the X-ray fluorescence microprobe beamline. His research focuses on the biogeochemistry of trace elements in soil and the rhizosphere and the interactions between soil microbes and higher plants that are relevant to climate and energy. Ryan holds an adjunct faculty appointment in the Department of Plant and Soil Sciences at the University of Delaware and serves on the External Advisory Committee for the Delaware Environmental Institute. Ryan, so you can take over. Yeah, we can see the slides well.
Ryan, you're muted.
Can you hear me now?
Yes, thank you.
Very good. Thanks for the introduction, Satish. Much appreciated. Yes, I'm admittedly a soil scientist, and I believe that because of that, I have emphasized low temperature geochemistry in my attempt to give you a facility update. So please forgive me, but hopefully some of the hard rock folks will bring in some of the missing bits. So most of you know to look for us out on New York, on Long Island, about 2/3 of the way out. You can, thanks to Google Earth, see some of the nice scars that some of our accelerators have left. This is the RIC facility. You squint really hard at this logo, you'll see the NSLS-II facility, which is also shown here as a cartoon map. And today, the NSLS-II facility has 29 operating beamlines. These can provide experimental stations that would range from scattering to imaging to spectroscopy. And there's been a clear emphasis in the last few years on this multimodality. So both beamlines that are multimodal themselves, but also the ability to do multimodal science across beamlines and across facilities. Now we're still organized by technique. So we have our geosciences distributed across several programs. I think the thrust of it is in the imaging and microscopy and the hard X-ray scattering and spectroscopy programs. But we do have a few contributions from the other programs that I reached out to. So I'll show you those as well. Imaging microscopy program is led by Young Chu here. He's our program manager. And we are operating a set of a family of microscopes that collectively cover a broad range of energy and spatial scales. So like you mentioned, I'm in charge of the X-ray fluorescence microscope, and that is predominantly a geoscience end station that's co-operated by GSC cars. But we also have TESS, SRX, getting into the submicron and then to the HXN nanoprobe, and then even a full field transmission X-ray microscope. In addition, we are conveniently located near our hard X-ray spectroscopy neighbors, and some of our community heavily relies on these techniques. So this is Eric Dorhe's program. He's the program manager for hard X-ray scattering and spectroscopy. A number of these beamlines should be familiar. XPD is a routine technique. Many of us are doing PDF, XAFs for materials, XAFs into quick mode, full-blown intershell spectroscopy with emission type capabilities. And Eric's program is also building up the hex beamline, which I'll mention in just a second. I'll point you back to the corner to say we're all nested together near LOB3, and we have a number of labs that are there to support the beamlines, because geochemists need labs. You don't want to see a chemist without a lab, right? So we have some pretty well-equipped biogeochemical support laboratories adjacent to the beamlines. We have everything from inert atmospheres to ovens and things you can do to your sample before you bring it right out the hall to the beamline. We're even tooling up a cryo sample prep laboratory for the BER bioimaging project that'll have some cryo slicing tools and a few other bits, plunge freezers and the like. And then of course, there's other ancillary labs nearby that allow folks to prepare their samples for X-ray absorption spectroscopy or even do some wet chemistry if that's needed. So that's all nearby. This slide I stole from the strategic planning workshop a couple of years ago, where Tony Lanzarotti and I were asked to kind of work with the user community at NSLS-II and try to identify some capability gaps for the biogeochemistry community. And that's sort of where we ended up, was looking at some holes in the NSLS-II program. And certainly the STIXM was a big hole identified by the user community, but also by micro-CT and tender X-ray nanoprobe type of instruments for imaging. So, but to our surprise, I think one of the biggest responses we got was we need more capacity for the instruments that we do have. We can't get enough access. And that's partly what drives the multimodal measurements across facilities, I'm pretty sure. But then there was also a few other requests. And so looking a couple years later, I'm getting this right off our NSLS website now, are the beamlines that are currently under development by NSLS-II. And a couple of those I've highlighted here because I think they hit on some of the needs of our community. Certainly the hex beamline with the hard X-rays well above 40 to punch through all sorts of, sample cells and devices and to look at buried interfaces. They'll have some imaging capabilities for tomography and 3D imaging, as well as some basic techniques like powder diffraction and NPDF. And the XSN microscope is very much like a nanoprobe coupled with a STXM. So it's really shooting for imaging and spectroscopy tools from carbon to sulfur in that energy range that would really be considered soft and tender. Some important M&L edges you heard everybody talk about down in that energy range as well. Okay, I want to shift gears for just a second and give one example from the XFM beamline. This was a multimodal science project that was led by the University of Sheffield. And they also used the diamond light source beamline. And at both facilities, they coupled the XRF, XRD, and XAS technique. So these were lava-like fuel-containing materials that were simulants for what's in the reactive core of Chernobyl. Notice the XRF images, they give you element-specific maps. You're all familiar with that. Here, they're just showing us a nice co-localization of uranium and zirconium. They're not telling us they're chemically associated, but they seem spatially associated. The micro-XRD work here was actually done at Diamond in an imaging modality, and this provided the crystalline phase assemblages of the fuel simulants, which included this Chernobylite and some other compositions in the uranium zirconium solid solution. But the majority of the material is really this amorphous glassy matrix that's loaded with uranium, and diffraction techniques are just not going to provide the contrast to study those. So here's where the micro-XAS technique at the XFM beamline became an important part of the study, and as well as the imaging, because they provided detailed information about the local coordination of environment of uranium in those matrices, as well as the crystallites. So long story short, we've got a combination of techniques used to really obtain insight into the fuel chemistry in this scenario, which hopefully can inform designs to contain or decommission it. So that was the one science example I wanted to drill down on, but I do have a few other things I want to kind of highlight. One is, I think, coming out of this, the workshop that Tony and I led was that geochemists across the board need X-ray spectroscopy. And I won't talk much about the science here. This was one of the NSF Coastal Seas projects led by Don Sparks at the University of Delaware, where I'm also affiliated. And it's turning out to be one of our heavily cited papers, but that's as an aside. What was so cool here is we needed to use micro-XAS to really understand the bulk XAS. And we did this experiment across facilities as well. So this was done partly at Stanford and partly at the NSLS-II, kind of drilling down to that finer scale. Which leads me to an example that I want to tell you about HXN, which is our nanoprobe beamline that routinely delivers less than 10 nanometer resolution with the multi-layer Lowy lenses and less than 50 nanometers with the zone plates. And you can see they have multiple modes of contrast here: diffraction, fluorescence, transmission. So a lot of ways of doing imaging and getting contrast through those modes. Here's some work that's early on by Ajit Padamatel on our group, who's looking at nanoparticle pyrite and single particle oxidation of that using the nanoprobe. So some pretty exciting work that's just getting started with Ajit at that nano scale. And also state claim that geochemists, and I think I'm preaching to the choir here, we need soft and tender spectroscopies as well. And certainly for folks like myself in the low temperature biogeochemical game, there's a lot of feedbacks in the biogeochemical cycling of these elements. You know, we can't really look at carbon without looking at iron, and sulfur is an important part. So we have some microscopes that are coming online that I mentioned that would give us carbon spectroscopy at the nanoscale. We already have some bulk spectroscopy for carbon edge at the SST beamline. I don't have an example to show you, but I can put you in contact with folks that can make the measurements at the carbon edge. You already heard from Paul and Tess. XFM can also do sulfur K edge, but cannot go any lower down to the phosphorus edge. I won't say much more about Tess because you heard all about it from Paul, but just to say we do a lot of multimodal work between the microprobe in the hard and tender energy range. This is just one example in planetary geosciences where we needed to confirm a rare iron sulfide mineral in the system that spectroscopy had alluded to. And so we used XFM hard X-ray diffraction to really finalize that identification of that mineral. But a lot of opportunity for geoscientists to do work with tender X-rays. And even low T folks like myself need custom sample environments. And these are a number that we see here at the microprobes at NSLS-II, but I'm sure you see a number of them across the complex. The diamond anvil cells are fairly common. Microfluidic devices are becoming more and more common. This one I'm showing you here is from Leslie Shore at the University of Connecticut, who actually used computed tomography to get a natural pore network and then mimic that in a PDMA device. They're looking at simulated groundwater systems with reduced arsenic. Ecosystem sciences, I'll say a few things about that. In fact, let me just give you a few flavors of the work that's been going on in the custom environment. So here's one I just want to quickly point to, and if you're more interested, follow up with this paper by Chen and Kokar. But they're using another type of a microfluidic device that's been etched out of silicon, where they can make very tight constraints on the pore system and then do hypothesis testing. And in this case, they're looking at iron oxide precipitation in real time. And then they're coming back with some tracers like bromine or contaminants like arsenic in various flushes to see what kind of mineralogy formed in which compartments and so on. So this is some of the work that started at Stanford and then wrapped up at NSLS-II and was just recently published by Kokar and company. And some other work on in situ environments that our community tends to the really low temperature geochemistry maybe is more of the biogeochemistry side, where we might want to do imaging of some really delicate samples or that have redox sensitive elements like arsenic. You know, in this example, we're actually measuring a fern that had arsenic in it. And you can see in the bottom left corner, when we do that at room temperature, we induce the chemistry that we're measuring. But if we do that at cryogenic temperatures, we can actually capture it before it transitions to the arsenic 5. And this is a newer environment that we're working on with BER, and some collaborators of mine are studying ectomycorrhizal fungi. We've heard some other talks about the rhizosphere today and some of the cool things that are happening there. And we were looking at coupling omics and fluorescence imaging and some other techniques to really understand the mechanism of iron mobilization at the plant microbe interface. And so this is one of the microcosms that we put together with a model soil system to constrain the speciation and then start to look at how things change over time. And I'll just spend a second on this, even though this is a facility update, I have to take the opportunity to tell you a little about science. In the case with the ectomycorrhizal fungi, you get these cool forked roots. Those don't show up when you have no ectomycorrhizal fungi. And you get this really thick mantle of iron that glaces the epidermis of the infected roots, which you don't see. But more interesting here, the grains, they stay intact. After 2 months of growth in this system, they pretty much look like the way we put them into the system. But a couple months later, they disintegrate when you have the fungus in the system. And you can poke around these forked roots and look at the iron speciation and notice it's all iron 3, and that's not what we expected, but we've checked and checked and checked again, and it's all iron 3 everywhere we look, with one exception of the plant root itself. And so what we're finding is that the plant has pumped a bunch of oxalate out into, or the fungus has pumped a bunch of oxalate into the rhizosphere, which other researchers have observed in the past. And this oxalate is at various stages bound with calcium, and in other stages it's free. And we believe that this mechanism is related to iron acquisition, because when we explore the iron speciation in this rhizosphere, everywhere we look in the fungal mantle, we find the same iron 3 complex. It's very similar to iron oxalate or hydroxamate, but it's definitely some sort of a small low molecular weight iron compound that stabilizes iron in this iron 3 oxidation state, which is kind of fun because we think we have evidence, and I'm trying to animate this over here in real time, that we have a ligand promoted dissolution mechanism that's not reductive. Again, this is not what we expected. Stum described this mechanism years ago as that fast intersphere absorption. Here I show it as a monodentate to bidentate chelating, but then it's that kinetically slow step for it to detach before it finally plucks apart the mineral 1 bit at a time. And that's what we think we're seeing in this in situ microcosm. Forgive me for dabbling in the science. I have a couple quick things to show you that came in from the other 3 programs when I asked, hey, who's doing geosciences? And infrared spectroscopy, we did hear one other mention of them today, and it's great that it's non-ionizing radiation, so you can really look at live systems and then come back and look at them again. Kind of not like what I'm telling you about the previous study. But certainly here we've got some instrumentation that's been used in the past. You can see in the bottom right corner, there's pretty small to see, but there's some papers that have been put out, interface work, looking at minerals, clays, and water, often in the case of the IR techniques. And here's some more recent work in Nature Geosciences that they're bringing up about the kaolinite and the deep water cycle that might be worth looking into if you're considering this kind of geoscience. One other one I got from another program was the SAX-WAX folks who are doing mostly material science, but there was one particular group at Princeton. It was Bastien Wild who's using this technique of GSAX to look at the surface alteration layers and really get some information about properties at the mineral water interface using this technique in a fluid flow cell type system. So that's pretty exciting stuff going on at that beamline. And lastly, this is a little bit disconnected, but it was pretty cool and novel. The LIX beamline, which is in the structural biology program here, is doing some scattering in a mapping mode. And they've been looking at cotton and cellulose and some other biofuel stuff. And they're starting to get images that they can quantify. And they can get abundance of cellulose and crystallinity indexes, even rotating the sample and doing some image reconstruction like you would in conventional tomography. So there's some pretty cool developments going on at LIX when it comes to using scattering in this mapping mode. So that's all I was able to gather from everybody at the facility in a short time. Hopefully at SES we'll have some more updates for you. But just to remind you, come see NSLS-II. This is our director, John Hill. Come meet him and come see our facility and see if you can do some cool science with us. Thanks.
Okay. Thank you, Ryan. Any comments, questions?
We're getting tired.
Trying to access the chat, so just give me a second. Okay, so there is a question from Angela Halfpenny, and the question is there a Maya detector for the XRF beamline at the NSLS-II, or has this detector been surpassed by something new?
There is a Maya detector here, and it is currently going through an upgrade to an SDD version. So it's typically been a silica diode based array, and now it's going to be a silica drift diode array, and that will give it some improved energy resolution on the order of, say, 150 EV, full width, half max. And that makes it competitive with some of the commercial detectors, but it will also have that high dynamic range that sets it apart from the rest of the crew. And in particular at XFM beamline, I didn't mention a lot that we also have a pink beam imaging capability where we can put like 10 to the 14 photons in a micron spot and really do some damage if you want. But conventional detectors won't keep up with that. And we really need the Maya or Maya 2 to deal with that dynamic range. And so we'll see a new detector coming to XFM beamline just to deal with the pink beam imaging part of the experiment very soon.
All right, thank you. Another question from Ludmila. So it's actually the same question I also have. And this is regarding the iron 3 or iron 2 phases. Which specific class of organic compounds from the roots were associated with it? I know you showed this, like beautiful map, and you talked about Stum's version and so on, but you didn't comment about the details. You are muted, Brian.
Thank you. We don't see any iron 2 species in this system at all, with one tiny, tiny exception.
Sorry, I think she meant iron 3, so not iron 2.
Oh, okay. So the iron 3 species is an iron 3 oxalate or hydroxamate-like species.
Yeah, from the XFs, you should be able to identify the difference though, right?
No, you should, but that's the difference between a carbon and nitrogen in the second shell versus 2 carbons in the second shell.
Yeah, I mean, also it depends on whether you have hexadentate versus bidentate, right? So
yeah. Now I will say we do see a tiny bit of iron 2 well far away from the fungus at the epidermal region of the root. This is done with an iron 2 mapping mode. It's the only place after 2 years of looking that we've been able to find any reduced iron in this system whatsoever. But it does suggest that there's a pool of iron 3 chelators that are formed by the plant fungal interaction that are bathing the root, much like a hydroponics system. The plant can cause that reduction at the root surface of the iron 3 chelator to an iron 2 species that can be brought into the root and go up as an iron 3 citrate actually in the end. So it goes back to iron 3 when the plant brings it into the vascular system.
Okay, thank you. So thank you, Ryan,
Yes.
for a great talk and beautiful images. So we'll move to
Thanks.
the last talk of the day.